Friends, it is a known fact that electrical networks are subjected to switching on or off very often. For example, a network which is not energized for a long time might be switched on by applying excitation. Similarly, the network which is energized long back might be suddenly switched off. It is common and is a necessary operation in electrical systems. Further, the network in operation might by itself may become off due to some unforeseen reasons such as short circuits or overloading and so on. But it is interesting to note that all circuit elements will not behave in the same manner when they are switched on or off. This is true particularly for energy storing elements such as inductance and capacitance. Therefore, it is necessary to analyze the behavior of network and network elements under such conditions. We know that any physical system analysis need to be predetermined using mathematical approach, and very important aspect is for analyzing the performance under normal or under abnormal situations, the system has to be transformed into a mathematical model. Friends, the mathematical model of most of the physical systems, no matter it is electrical system or mechanical system or chemical system and so on, turns out to be a differential or integral differential equation. Therefore, engineer of any branch need to have the knowledge of basics of differential equations, the types and their solution. Of course, in mathematics course, these details are covered. But before we start the study of the performance analysis of electrical networks, a brief review will help better understanding the results obtained.
Friends, in this short tutorial, we shall seek answers to the questions such as what is the differential equation, how to identify the order of the differential equation, what is ordinary differential equation, and what is linear differential equation, and finally, what is homogeneous and non-homogeneous differential equation. For that, consider a simple RL circuit excited by a DC source as shown in figure. After the switch K is closed, the system equation for the response I in the circuit can be written as R into I plus L into di by dt is equal to V. Let us seek answer for question number 1. That is, what is the differential equation? A simple answer for that question could be a differential equation is any equation which contains derivative terms. In this equation which we have obtained, there is a derivative term di by dt, hence this equation can be called as a differential equation. Then, how to identify the order of the differential equation? Friends, you know the order of any differential equation is the power of the largest derivative term that the equation contains. In this equation that we have obtained, the largest derivative term is di by dt and its power is 1. Hence, this equation can be called as a first order differential equation. Hope this is clear to you. Now, let us see what is ordinary differential equation. A simple answer for this question could be an ordinary differential equation is one which has ordinary derivatives in it. I mean, it will not contain any partial derivatives. If you look at the equation for RL circuit that we have obtained, it does not contain any partial derivatives, hence it is ordinary differential equation. Then, What is a linear differential equation? Friends, a linear differential equation with constant coefficients is any differential equation which can be written in the form an into nth derivative of I with respect to t plus an minus 1 into n minus 1th derivative plus etc. plus a1 into di by dt plus a naught into I is equal to v of t. The equation of this type is called as linear differential equation because it does not contain any terms of type product of function I of t. What does this mean? A product of type I of t into di by dt is the product of the function I of t. If you observe the equation above, all the terms are multiplied by constants such as an minus 1, etc., a1 and a naught. Hence, friends, remember, a linear differential equation is one which does not contain any terms of the type product of functions of I of t. If you observe the equation for RL circuit that we have obtained, we can call this equation as linear differential equation because it does not contain any product term of type I into di by dt. Also, this equation can be called as a linear differential equation with constant coefficients since all the coefficients of I and its derivatives are constant terms. Friends, now let us understand to identify the homogeneous and non-homogeneous differential equation. The differential equation is said to be homogeneous if the term phi of t in the system equation is 0, meaning the term phi of t should be free from the independent variable I or its derivatives. On the other hand, if phi of t is not equal to 0, then the differential equation is said to be non-homogeneous differential equation. Again, if you look at the equation for RL circuit that we have obtained, it is a non-homogeneous differential equation because the term phi of t is present. In conclusion, we can say that the equation for RL circuit that we have obtained is a linear, ordinary, first order, non-homogeneous differential equation with constant coefficients. Now, let's differentiate this RL circuit equation. By differentiating it, we get R into di by dt plus L into d squared I by dt square is equal to 0. Note that phi is constant and hence its derivative is 0. By rearranging it, we get d squared I by dt square plus R by L into di by dt is equal to 0. Let us analyze this equation. This equation is ordinary differential equation because it does not have any partial derivative terms. It is linear because it does not have any product terms of the function I of t. The coefficients of I of t and its derivatives all are constants, hence it is a differential equation with constant coefficients. It is a second order differential equation because the largest derivative term is d squared I by dt square. It is homogeneous because the forcing function on the right hand side is 0. Hope you have understood how to identify the type of equation. Now, consider an RC series circuit connected across a DC source as shown in figure. Let it be required to obtain the equation for the system response after the switch K is closed at t is equal to 0. So, For t greater than or equal to 0, the equation can be written as r into I plus 1 upon c into integration I dt is equal to v. Friends, look at this equation. Can we call this equation as a differential equation? My answer is no, because the equation contains the term integration of I into dt. In fact, this equation can be called as an integro-differential equation. Hence, by differentiating this equation, we get r into di by dt plus I by c is equal to 0. By rearranging it, we get di by dt plus 1 divided by r into c into I is equal to 0. Now, can you identify this equation? Yes, friends. It is a linear, ordinary, first order, homogeneous differential equation with constant coefficients. Next, consider an RLC series circuit connected across a DC source as shown in figure. After the switch K is closed at t is equal to 0, the system response equation can be written as R into I plus L into di by dt plus 1 upon c into integration I dt is equal to v. Again, you see that we have arrived at an integral differential equation. Hence, by differentiating it, we get r into di by dt plus L into d squared I by dt square plus I divided by c is equal to 0. By rearranging it, we get d squared I by dt square plus r by L into di by dt plus 1 upon LC into I is equal to 0. This equation is a linear, ordinary, second order, homogeneous differential equation with constant coefficients. Hope you have understood how to write and obtain the differential equation and identify its type. Now, let us consider another example to obtain the differential equation for the current in the circuit after the switch K is closed at t is equal to 0. You see that when the switch K is closed, the forcing function I becomes 0 as it is going to be short circuited. Therefore, by writing the system equation, we get R into I plus L into di by dt is equal to 0. By rearranging it, we get di by dt plus R by L into I is equal to 0. This equation turns out to be a linear, ordinary, first order, homogeneous differential equation with constant coefficients. Similarly, consider another circuit shown in figure wherein the switch K is at position A for sufficient time till the steady state is reached. Then the switch is moved from position A to position B at t is equal to 0. We are required to find the system equations in both the cases. First, consider the case when the switch K is at position A. We find that R and L are connected across a DC source of 10 volts. Therefore, the system equation can be written as 10 into I plus 5 into di by dt is equal to 10. By dividing the entire equation by 5 and rearranging it, we get di by dt plus 2I is equal to 2. You see that this equation is a linear first order non-homogeneous differential equation with constant coefficients. Next, we shall consider the case when the switch K is moved to position B at t is equal to 0. So, for t greater than or equal to 0, the system equation can be written as 10 into I plus 5 into di by dt plus 1 divided by 0.2 into integration I dt is equal to 0. You see that this equation also turns out to be an integral differential equation. Therefore, By differentiating it, we get 10 into di by dt plus 5 into d squared I by dt square plus 5I is equal to 0. By dividing throughout by 5 and rearranging it, we get d squared I by dt square plus 2 into di by dt plus I is equal to 0. Now, you see that this equation turns out to be a linear, ordinary, second order, homogeneous differential equation with constant coefficients. Friends, in this short tutorial, we have learned how to write the system equation for the response for a given circuit and to bring the equation in the proper form of a differential equation. We also have learned to identify the type of differential equation obtained. I feel that this tutorial helps to lay a strong foundation for the study of transients in electrical networks. Of course, the discussion in this tutorial is limited only to obtain and identify the differential equations for the circuits. We shall take up the solution of first and second order differential equations in the subsequent tutorials. I assure you that the solution will be made simple by avoiding rigorous mathematics. I hope this tutorial has kindled some of your thoughts. If so, please forward your feedback and suggestions to my email. Thank you for watching this video.